Okay, now this one is page 21, June 2017 P41. You have a bar magnet of mass 180 grams that is suspended from the free end of a spring as illustrated in this figure. A magnet hangs so that one pole is near the center of a coil wire. The coil is connected in series with a resistor and a switch. The switch is open. Then the magnet is displaced vertically and then allowed to oscillate with one pole remaining inside the coil. The other pole remains outside the coil. At time t equals to 0, the magnet is oscillating freely as it passes through your equilibrium. At time 3 seconds, the switch in the circuit is closed. The variation with time of the vertical displacement y of the magnet is shown in figure 2.2. Up to this point, you have constant amplitude. So there's no damping here because the amplitude did not drop. But from there onwards, you will notice that your amplitude drops. This one here, you're going to have decreasing amplitude. There is damping because you can see from here the amplitude is dropping. Unlike the ones before, the amplitude was actually constant. So there's one thing here that you can actually identify from here. So determine the two significant figures, the frequency of oscillation of the magnets. So this one shouldn't be that big of an issue. Find out the period, then find the omega. This is one complete oscillation, right? So your period is 1.2 seconds. The one frequency, right? Frequency to two significant figures. You can actually just say is the reciprocal of your period. So it's 1 divided by 1.2, giving you 0.83 hertz. Specifically, the question requested 2 SR. Don't write it to 3 SR. There's another way to do the same question also, but I think it's a bit more tedious. To find frequency, you take the number of oscillations, divide by total time. In my case, for this particular working, I found out that for 7 cycles, the time was 8.4 seconds. So I actually counted a number of cycles here. I calculated 7 cycles. So this is 1, 2, 3, 4, 5, 6, 7. So I calculated 7 cycles and I found the corresponding time, and then I used this equation to find the same frequency. Okay, but I think this is a bit more tedious now. All right. Now, for part B, state whether the closing of the switch gave rise to light, heavy, or critical damping. Just now, right over here, the closing of the switch was at 3 seconds. If you read the question, they mentioned to you that the switch was closed at 3 seconds. So at 3 seconds, it was actually here. This is the part where your switch was closed. That's where your amplitude started dropping already. So here the question just really wanted to know whether the act of closing the switch gave you light, heavy, or critical damping. So one of the things that you can actually see here is that the oscillation was still maintained about the equilibrium position. Okay, oscillation is still maintained about the equilibrium position as the amplitude gradually decreases. So this one, you know, is going to be light damping. It cannot be heavy, it cannot be critical, because for heavy or critical damping, I mentioned to you, oscillations don't actually continue. It will actually just straight away go back to the equilibrium. Only for light damping will oscillation still be maintained as the amplitude gradually decreases. So that's for that. Okay, then the last one would be part C. Now for part C, it is extremely high in terms of the mark allocated. There's 6 mark allocated for this part alone. So calculate the change in energy, delta E, of oscillation of the magnet between t 2.7 seconds to t 7.75 seconds. Explain your working, all right? So all this requires 6 marks of working. In the first place, we go back to the basics. Energy total is CAIE max is half m omega square x naught square. So you want to find the energy loss between 2.7 to 7.5. So you're talking about 2.7. This is 2.7 seconds. This one is the amplitude. So at t 2.7 seconds, your x naught is 1.5 centimeter. At t equals to 7.5 seconds, that's the next time that you're interested in. At t equals to 7.5 seconds, your amplitude is going to be 0.75 centimeter. So these are the two amplitudes for the two respective timings. So all you just need to do is really to just sub these two values into this equation and then find out the difference in the energies. That's what you needed to do here. So in our case, your working now looks like this, right? So here you can see that E total energy is half m omega square x naught square, but because you don't have the value for omega, instead you have value for frequency that you found above. Your omega you change to 2 pi f. Then you start to tackle the values one by one. When t1 is 2.7 seconds, your amplitude is 1.5. So energy at 1 is half times your mass times your 2 pi f square times your amplitude change to meter, giving you this. Then you repeat again for the next timing. When t is 7.5 seconds, the amplitude is 0.75 centimeter. So the new energy is half times mass times 2 pi f squared times the amplitude change to meter, giving you this. And then finally, your answer will just be the difference between the two values. Now you may be thinking, can I just somehow combine everything in one single step like this, where I say delta E is E1 minus E2, so it's half m omega square x naught 1 square minus x naught 2 square, where you just straight away sub in your values, m 2 pi f square x naught 1 square minus x naught 2 square, and then after that you start subbing in your values. So it's 0.18 2 pi times with 0.83 square times with 0.015 square minus with 0.0075 square, giving you 4.16 times 10 power minus 4 joules. So if you're thinking of writing your answer like this one is also acceptable. But this one I won't recommend it because you see with 6 marks being allocated here, it'll probably be best for you to write everything step by step. If you combine everything in one shot here, if you make one mistake during your substitution, it may affect the overall workings here. So you might end up losing more marks because the examiner can't really seem to separate out which one was the thing that you did wrong. But if you separated out your workings like this, even if you were to make some careless mistake, the mistake is just isolated to one part of your workings. The examiner will just minus that part and can still mark the other part. But you combine everything in one shot like this, the moment you make one careless mistake inside, it may actually cause you even more marks deduction because the examiner is not able to determine certain things from your combined equation. Okay, so that's the gist of it. Okay, have a look at, say, page 31. So page 31, this one is June 18 P41. They mentioned that a plate is made to vibrate vertically by means of an oscillator as shown. Some sand is sprinkled onto the plate, and then the variation with displacement y of the acceleration of the sand on the plate is as shown here. Okay, this is for the sand right over here. They're giving you the graph of acceleration versus displacement shown like this. So in our current case, they ask you to use the figure to show how it can be deduced that the sand is undergoing simple harmonic motion. So this is your standard vanilla acceleration versus displacement graph. So you can actually see from this graph that this object is undergoing simple harmonic motion. So that time I told you A is negative omega square x. If you plot a graph of, say, A versus x, after comparing it to y equals to mx plus c, you should get straight line graph passing through origin with negative gradient. So from the equation A equals to negative omega square x compared to y equals to mx plus c, if you were to try and plot out the acceleration versus displacement graph, it will look like this. So it will be simple harmonic motion based on two things. If it's a straight line graph through origin, this means A is proportional to x. If it has negative gradient, this means A and x are always in opposite direction. So you're trying to do the same deduction here for your given graph to show that it's actually simple harmonic motion. So here you are basically following the same points. A straight line through origin indicates acceleration is directly proportional to displacement. And then a negative gradient indicates acceleration and displacement are in opposite directions. Then calculate the frequency of oscillation of the sand. So for your particular case, again, this one is something that I also kind of did mention before. If you compare your equation A is equals to negative omega square x with y equals to mx plus c, you will see that your gradient is actually negative omega square. So here, gradient is negative omega square. Then from here, they want the frequency, right? So gradient is actually negative 2 pi f square. So you find your gradient from the graph, and then after that, you equate it to 2 pi f. That is what is being shown here, like this. This is one part. This is using gradient. But I also did mention to you that you can use single point substitution, which is not shown in my working here. You find a pair of A and X from graph, then substitute into A equals to negative omega square x. This is another method that you can also use. Find a pair of A and X from the graph, and then substitute into A equals to negative omega square x. And just make sure that this one eventually you make it into a negative 2 pi f square x, because you want to find f in the first place, right? So you do the second method, not necessarily you always need to use gradient. It's just that in my case, I've always used gradient. All right. Now B is the one that's a bit different than the rest. This is the one I want to discuss with you. Now the amplitude oscillation of the plate is gradually increased beyond 8 millimeter. The frequency is constant. At what amplitude the sand is seen to lose contact with the plate. For the plate, when the sand first loses contact with the plate, state the position of the plate and then calculate the amplitude of oscillation. So here, there's something I just wanted to mention to you. Now let's consider a few cases. Your case here is that you have a plate and then you have some sand that is resting on the plate, right? Let's just say right now, your plate is moving up and down, up and down. If you consider at the top position, your plate has a certain acceleration. Your sand would also have a certain acceleration. So let's consider this. Your acceleration of your sand will actually be equal to g when it loses contact with plate. There are two objects here, the sand and the plate. For the sand itself, the acceleration of the sand down towards the equilibrium is actually equal to g when it loses contact with the plate, because at that time is only the weight acting, the weight of the sand acting. So the acceleration of the plate, this one can actually vary. This acceleration of the plate varies with displacement x. We know that A is directly proportional to x, right? So your displacement is large, your acceleration is large. If your displacement is small, your acceleration is small. Again, this is from your A equals to negative omega square x. All right, so this acceleration of plate here is referring to this. Okay, it varies with your displacement x, how far you are from your equilibrium position. If let me just draw for you your equilibrium right over here. This is your equilibrium. Now, let's consider this. If your A of your plate is actually less than G, what will happen is that your sand remains in contact with plate. Because what you're seeing here, it could be something like this. Say your A of your plate is 5 meters per second squared. But your sand, by right, if nothing is in contact with it, is equals to G, right? Which is equals to 9.81 meter per second square. So if anything, the sand would always fall faster than your plate. So it will always remain in contact with your plate. Here, I can always say that sand falls faster than plate. Therefore, it remains in contact with plate. Let's consider a second case then, where the acceleration of your plate is now more than gravitational acceleration. So what happens here then? In your current case, when this happens, your sand has lost contact with plate, because the idea here is, if this one is your sand, your acceleration of your sand is g, it's 9.81 meter per second square, but this one is your plate, the acceleration of your plate being more than g, let's just say this one is 15 meters per second square. This one, your plate is falling faster than your sand. So plate falls faster than sand. Therefore, sand is no longer in contact with plate. Okay, that's what you can actually see. Now, between this one and this one, these are the two extreme cases. If acceleration of your plate is less than your gravitational acceleration, your sand will still remain in contact. But on the other hand, your acceleration of plate is more than gravitational acceleration, your sand will start to lose contact with the plate. Okay, it's already no longer in contact with the plate. So where do you suppose is the point where your sand will start to lose contact? The point where the sand first loses contact. You see, the case is they say for the plate, when the sand first loses contact with the plate, the point of losing contact, your acceleration of the plate must be equal to g. So this one I'll write it here. If the acceleration of your plate is equals to g, the point where sand starts to lose contact with plate. You can call this the point of losing contact. So in my case, sand is here, its acceleration is equals to g. The plate is again here. The acceleration of my plate is equals to g. This is the point where your sand starts to lose contact, the point of losing contact. Just bear this in mind because you need to use this to do the last part of your question. So you look at part 1 first. State the position of the plate where your sand first loses contact with the plate. It should be at the maximum displacement upwards, no? Cannot be at the position below your equilibrium position. Cannot be at the maximum displacement downwards because logic will tell you you need your plate to be moving downwards in order for your sand to start to lose contact. Plate must be moving downwards for sand to lose contact. It must be moving downwards in order for your sand to lose contact. It cannot be your plate is moving upwards, then your sand starts to lose contact, right? It doesn't make sense at all. So your plate must be moving downwards in order for your sand to lose contact. Therefore, plate must be above equilibrium. Because when it's above equilibrium, that's where it starts to move down. So you can state any of these possible answers. It's above the equilibrium position, it's at the maximum displacement upwards, or it's just above the resting position. So this one, maybe I reword this. The plate must be above equilibrium so that it moves downwards. Okay, that's the proper wording here. Then for part 2, calculate the amplitude of the oscillation when your plate first starts to lose contact. So just now I already explained to you, your sand will just leave the plate. It's at the point of leaving your plate when its acceleration is 9.81 meters per second. The acceleration of the plate is 9.81 meters per second. So if you apply equation A is equals to negative omega square x, which is from here, you want to find the amplitude. This is what you want to find. So you use that same variation of your answer. A max equals to omega square x naught. You use this. This is what you're applying here. Your A, the maximum acceleration that you should have is 9.81. Your omega square, I actually already found it in my workings. I already know that omega square is actually 564.52. So find out your omega square, then multiply with y naught. which is your x naught, then eventually you get this answer. All right. So your amplitude at which the sand starts to lose contact with the plate is 17.4 millimeter. Right?